Welcome to day 5, video 5 of this AIM program. Hopefully you've been following along with all the previous videos and doing lots of useful math practice. Today is going to be about factors and prime factorization. So I'll explain what those are in a moment. In the previous video, we talked about long division and we went through lots of examples. Hopefully you have done a bunch of those examples and you can do that process quickly and sort of really learned how to do that if you forgot it. Today we will be talking about prime numbers first, and then divisibility tests, and then prime factorization. The vocabulary we are going to need, you can see here on the right: digit, even number, odd number, multiple, factor, and prime number. All right, so vocabulary first. We can see here digits. So digit is just like a single number in a larger number. So 555 has sort of 3 columns here. So this is a 3-digit number. And 12,321 is a 5-digit number because it has 5 parts, 5 columns. So we have the first digit 1, we have the last digit or final digit, also 1 in this case, like that. The other ones here, so even numbers and odd numbers, we have for an even number, anything that is divisible by 2. So that just means the last digit is a 0 or 2 or 4 or 6 or 8. And odd numbers are the opposites. They're not divisible by 2. So the final digit is 1 or 3 or 5 or 7 or 9. So even and odd numbers. Right, next ones. So multiples of something. So a multiple of a number is a number that can be evenly divided by a given number. So if we start with the number 5 and we say, what are the multiples of 5? Then, well, 5 times 1 gives us 5, and 5 times 2 gives us 10, and then 15 and 20. So these are all the multiples of 5. That, and factor, the other side of that, if we start with, say, 20, and we say, what numbers can evenly divide 20? By evenly divide, we mean not like even number from the previous slide, just means cleanly. So no fraction or no decimal result. So 2 will cleanly divide 20 because the result is just 10. It's not 10.2 or 9.5 or something, just 10, no decimal. So 2 is a factor of 20, so is 4 and 5 and 10. These are all factors of 20. Okay, so vocabulary here. So 2, 4, 5, 10 are factors of 20, or we could say 20 can be divided by 5, or we can say 20 is divisible by 5. So all 3 of those are ways of saying, or talking about factors. Okay, so let's get in with our first topic here, prime numbers. One more small vocabulary thing, a whole number. Whole number is just this set of 0, 1, 2, 3, 4, 5, 6, like this. So just on like that. So no decimals or anything, no negative numbers. Those are whole numbers. All right, so a prime number is a whole number whose factors are only 1 and itself. So for example, 2 and 3 and 5. So 5 cannot be cleanly or evenly divided by anything other than 1 and itself. So 5 over 4, that's a decimal. 5 over 3, that's a decimal. 5 over 2, that's a decimal, etc. Okay, so you know what these are. 7 and I'm going to let you do this. So try to list the first 15 prime numbers. The first excuse me, first 15 of them. I will go away for a moment and see if you can remember them, or if you can't, then figure them out. First 15. Okay, so the next one here is 11. That's not so hard. So that's the first 5. 13, 17, 19, yes. 21, no, that's divisible by 3 and 7, so not 21. 23 works. 27, no, but 29, yes. Okay, that's 10 of them. 31, 37, 41, yes. 43 and 47. Okay, there's 15, and these go on forever. There are an infinite number of prime numbers, but the first like 5, first 10, at least having those just sort of memorized, very useful when looking for factors, which is what we're talking about today. Okay, so let's get on with our actual practice here. So we'll come back to sort of using the prime numbers in a bit, but once we do this, we'll see the connection there. Divisibility tests. So is a number divisible by some other number? Well, we can say this number here, 5,625, is that divisible by 3, by 2, or by 3, or 5, or 6, or 10? We could, of course, just do long division, like with 3. So 3 dividing 5,625, and then that's 1, and that's 3, and 2, and 6, and etc. Like we could do this, but we can figure out the answer without actually having to do the division. And I'm sure we recognize some of these patterns, but I'll just go through all of them and make sure we're clear on what all the patterns are here. All right, so 2 first. So dividing a number by, is a number divisible by 2? So we kind of already talked about this. It's the even number idea. So if a number is even, then of course we can divide it by 2. So is the last digit a 2 or 0 or 2 or 4 or 6 or 8? Well, in this case, obviously the last digit is 5, so that's a no. So this number 5,625 is not divisible by 2. Do our next one, 3. If we want to know if it's divisible by 3, then we here can add up the digits. So take each digit separately. So 5,625, so 5 plus 6 plus 2 plus 5, and that is equal to 18. And then we look at this number and we say, is this number divisible by 3? If the answer is yes, then okay, then the original number is, and if it's not, then the original number is not divisible. And if this number, 18 is not very hard here, it's just 3 times 6, but If it's really big and we can't figure this one out, then we can just do it again and say, okay, 1 plus 8. Add up those digits, and that's 9. And keep going until you get a number that's small enough and easy enough to work with. All right, so 3, yes, divisible by 3. Let's talk about 6 next. So dividing by 6, then we just check if it's divisible by 2 and by 3. So 6 is the result of 2 times 3. So if we can divide by 2 and by 3, then automatically, yes, we can also divide by 6. So any number that's sort of a result of 2 other numbers multiplied together, you can just check for divisibility of those things. So in this case, it is divisible by 3, but not by 2, so not by 6. All right, so 5 and 10 are quite similar. Here we are just looking at the last digit. So if the last digit is divisible by 5, so it's just if it's 0 or 5, then the whole number is divisible by 5, and if it isn't, then the original number isn't. So this one, last digit is a 5, so yes, obviously. And last one, 10, same idea, just last digit. Only one possibility here, last digit needs to be 0, and if it is, then of course we can divide by 10. In this case, it's not, so, and not divide by 10. 5 and 10 are a group. Right, so those are the easier ones, but let's just, it's good to be able to do this again quickly, be able to recognize this stuff very quickly and try to look for common factors and such, which we will do in a few examples. So that's how we check, and let's do some practice. Let's take this number here, so pen tool, 4,962, and we say, is this divisible by 2? Okay, last digit's a 2, so by 2, yes. By 3, 4 plus 9 plus 6 plus 2. So if the digits themselves, 9 and 6, these are already divisible by 3. So adding those to whatever thing we're adding up isn't going to change the result. I don't even need to add these ones. I can just look at the digits that are not divisible by 2. Sorry, not divisible by 3. So 4 plus 2 is 6. So that is divisible by 3, so 3. Yes, and it's divisible by 2 and 3, so yes, it must be divisible by 6. By 5, last digit's a 2, so no. By 10, last digit's not 0, so no. Done. So if you need to write something out, great, but if not, if you can do these in your head, then that's fine. That's my turn, and now your turn. Okay, so this one, the answer here by 2, no, but by 3, yes. So by 6, no. By 5, yes. And by 10, no. Hopefully you got the same result. Next part, this one is, the next 2 sets are not from our textbook. You can just look at the examples that are here in case you're following along that way. So this number here, and is it divisible by 4 or by 8? So 5,628. So the tests here for 4, we look at the last 2 digits. If the last 2 digits are divisible by 4, then the whole number will be divisible by 4. So in this case, the last two digits are 28. And yes, that's divisible by 4. That's 4 times 7 would give us this number. So then the whole number will be divisible by 4. The other one, 8 here, quite similar, but we look at the last 3 digits. So in this case, we have 6 to 8. Last 3 digits. 6 to 8 or 628. If this number is divisible by 8, then our whole number will be. We might not be able to immediately recognize this, but we can also do this just sort of in parts here. So 8 is obviously 2 times 2 times 2. So we can check for divisibility by 2 just a few times and see what we get. So we can divide this by 2 twice, obviously, because it is divisible by 4. So we can at least do that much. If we split this up, we would get 300. Let's do this on the other side. 2 and then 314. 2 times 314 gives us 628. Okay, so we can split it up again. So this would be, sorry, not 2. This would be 100. 2 on this side, and on this side 157. Okay, so there's dividing by 4, but then 157, 7 not divisible by 2, so not going to be divisible by 8. So 4 yes, but 8 no. If you can directly recognize it, great. If not, and there are other shortcuts to make this a little faster, but this tree pattern is very reliable here. Okay, so next practice here, 4,968. Is this divisible by 4 or by 8? By 4 here, our number would be just 68. And yes, we can divide that by 4. That would be 17. So 4, yes. By 8, 4, 9, sorry, not 4, just 9, 6, 8. And is that going to work? So I would sort of look at 1,000 and then count down from there. That's one way of doing it, but we could also just make our tree thing again. So divide by 2, and we would get 484, and divide by 2 again, we would get 2 and 242. And then we can divide by 2 again, yes, 121. Okay, so we can divide by 2 3 times, so yes, divisible by 8. Okay, so that's my turn. And your turn with this number, 3,752. All right, here the answer is by 4, yes, and by 8, yes. Hopefully you found that it's divisible by both of those. All right, next part. One more set of these. Yep, then we'll get on to the prime stuff. So divisibility by 9. If we want to know if a number is divisible by 9, then we just add up the digits, very similar to what we did for 3. Add the digits, and if the result after adding is divisible by 9, then the whole number is divisible by 9. So 5 plus 6 plus 2 plus 5, we already did this. We saw the result is 18, and okay, 18 is divisible by 9. So yes, the original is. Just in case if we did this and we got a very large number that's hard to look at, we can just do it again. 1 plus 8 is 9, so yes, 9 works. Okay, so very, very simple here. Just still add the digits. Let's do my turn here for this number. 4 plus 9 plus 5 plus 6. Again, as I mentioned, in this case, if we have a 9 in the number, we don't need to actually count it, add it into our sum, because it's not going to change the result. It won't change if the result is divisible by 9. If we included it, we would get 27, and if we don't include it, we will get 18, and those are both divisible by 9. So it doesn't actually change what we're doing. I'll do the shorter one here. So 4 plus 5 plus 6, 18. Yes, divisible by 9. Okay, that's my turn. And your turn with this number, 3,771. All right, the result here is that yes, divisible by 4, and also yes, divisible by 8. So hopefully you got the same result there. All right, next, so last set in this part, and then we'll talk about prime factorization. So divisibility by 9. To check for divisibility by 9, we do the same thing that we did for divisibility by 3. We just add the digits together. So in this case, we have 5 plus 6 plus 2 plus 5, and that result is 18. And 18 is divisible by 9, so yes, the original number will be divisible by 9. Again, if we want to know the actual results, we have to then do long division or something, but at least we can know in advance if we should bother doing that. Just like doing divisibility by 3, if by chance the result here of adding the digits is a large number that's hard to work with, we can just repeat the process. 1 plus 8, 9, obviously divisible by 9, so yes, the original number is. Okay, so that's it for 9. Very similar to 3. Let's do my turn here, which is number 4 plus 9 plus 5 plus 6. So just like with the 3s, I don't need to actually add 9 and check that because it's not going to change the result. But let me just show you that quickly. So if we added these up, then that's 13, 18, and 24. And the result, and the other way, if we left out the 9, then the result here would be 15. So both are not divisible by 9. They're also, they'd have the same remainder if we did divide them by 9. So that's where we can see the similarity. So not divisible by 9, so the original number not divisible by 9. All right, that was my turn. So now your turn with this number, 3,771. All right, our result here is yes. So hopefully you got that same result and found that it is divisible. Okay, so the next set of questions is about prime factorization. We'll have 4 sets in here, I think. So the first thing that we'll talk about is just what prime factorization is. So not like really tricky or whatever. We just want to find all of the factors of a number and factor it as much as possible. And naturally, when we do that, the final factors of the number will all be prime, because if it's not a prime number, that means we can still factor it more into something else. So we just take our number. Again, remember the prime numbers. So 2, 3, 5, 7, 11, 13. Usually we don't need many more than this. So 48 here. We'll just use our tree pattern kind of diagram here. So just go with the lowest prime number, 2, and keep dividing by that until you can't, and then stop, and then do by 3, and then by 5, etc. So in this case, 2 and 24. And let's try to divide by 2 again. Yes, we can. So 2 and the result 12, and divide by 2 again. Result is 2 and 6. So we can still do 2. So 2 and then 3. Okay, prime, 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 prime. All the factors that we have now are prime numbers, so we're done. So that means prime factorization of 48. This 48 is equal to 2 times 2 times 2 times 2 times 3. Or we could also write this as 2 to the exponent 4 times 3. That's it. So just, this is a simple example. We'll have some simple practice and then some larger numbers. There, erase. So my turn here with the number 80. So 80 is 2 and 40, 2 and 20, 2 and 10, and 2 and 5. Lots of 2's here. So that's 2, 2, 2, 2, 5. Okay, so there we go. If we want to check our work, just, actually multiply these together. So 2 times 2, 4 times 2, 8 times 2, 16, 16 times 5, 80. Yep, okay, right answer. All right, that's my turn, your turn with 60. So still pretty simple here. We'll go for more complex ones in a moment. Okay, so 60 here is equal to 2 times 2 times 3 times 5. Hopefully you got the same result. All right, next one, still exact same thing, just with slightly larger numbers. So we'll follow the same process. 252, we're going to divide by 2, and that will give us 126. And divide by 2 again, which will give us 63. Okay, so 2's are done. Now we look at the next one. So 3, and we divide this by 3, and we would get 3 and 21. Okay, we can still divide by 3, so 3 and 7. And 7's a prime number, so we're done. These are all prime. So our answer here is 2 times 2 times 3 times 3 times 7. Okay, I'll do, I know it's still just not too hard. Still keep our pattern here. I will do one for myself and then one for you. 195, 2 no, but 3 yes. This would give us 65. 3, no. Okay, so 2, 3 done, 5, yes. And if we divide this by 5, we get 13. And 13 is a prime number, so that's done. 3 times 5 times 13. All right, your turn with this one, 294. All right, we're back. So answer here, color is just 2 times 3 times 7 squared, or 7 times 7. Hopefully you got the same result. All right, let's go on to the last 2 sets of examples, trying to actually put this into use and do something practical with it. Finding a least common multiple for 2 numbers. So just to remind you, least common multiples, useful in lots of places, but for example, if we were doing addition, like something over 24 plus something over 36, we would want to change the 24 and the 36 to be the same, multiplied by the same something on top and bottom. We need a common denominator. So finding least common multiple is very useful there. A common multiple, a common denominator for 24 and 36. A multiple would be just, we could find by just multiplying the 2 of them together, 36 and 24. In this case, that's a pretty big number, 864. So maybe let's not do that. Let's try to find a more clever method here. So first, we'll list the prime factors of each of these 2 numbers. So 24 prime numbers. I'm not going to write out the tree thing. I'm just going to kind of do this in my head. If you can, that's fine. So 2 times 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. All right, and 36 is 2 times 18, and 18 is 2 times 9, and 9 is 3 times 3. Okay, so if I write these out, 24 like this, 2 times 2 times 2 times 3, and 36, and I'm going to make these line up 2 times 2 times, line up with the same numbers, so 3, and then we have an extra 3 there. So if we do that, then our least common multiple will be the number that we get from just kind of sampling each column once. So 1, 2, 3, 4, 5 columns like this. 2 times 2 times 2 times 3 times 3. 2 times 2, 4 times 2, 8 times 3, 24, and times 3, 72. So our least common multiple here will be 72. That's 24 times 3, 36 times 2. Okay, so it would be something over 72 plus something over 72. So we just write out kind of the prime factors, make them all line up like this, and then just 1 from each column will give us the least common multiple, guaranteed. All right, let's do another example. So this one for me, 21 and 28. 21 is not 2, but 3 times 7, and those are both prime, so that's done. And 28 is 2 times 14, which is 2 times 7. Okay. So there we have 21 and 28. So 2, 2, and 3, and 7. So not a whole lot of overlap here, but we do have kind of, gives us 4 columns like this. We do have overlaps with the 7. So makes our least common multiples at least a little bit smaller than just directly multiplying the two numbers together. So least common multiple, 2 times 2 times 3 times 7. 2 times 2, that's 4, times 3 is 12. 12 times 7 is 84. So there's a least common multiple between these two numbers. All right, last one. Or sorry, that was my turn, so your turn now. Here, least common multiple between 24 and 32. Okay, the answer here, what I got was least common multiple. I got 96. 24 times 4 and 32 times 3. Okay, so that's one thing we can do with this. Another thing we can do is find the greatest common factor. Greatest common factor is, of course, useful. Let's say if we have a fraction like this, 54 over 36. If this was a fraction, we would want to find the greatest common factor to reduce this. So again, when we write this out, we kind of writing a bunch of stuff to make sure the process is clear for you, but when you actually do this for yourself, you would probably write it in a much shorter and faster way, which is fine. This is meant to be a shortcut. So 54 prime factors, again, we're going to write those out. So 54 is 2 times 27. 27 is no 2 there, but 3. 3 times 9, and 9 is 3 times 3. And 36 is 2 times 18, and 18 is 2 times 9, and 9, 3 times 3. Okay, so we're going to do the same thing as before and write these out. 36, 2 times 2 times 3 times 3. And 54, 2 times 3. Make sure everything lines up. 3. Okay. So we see 1, 2, 3 spots where we have a common factor. So to find the greatest common factor, we're just going to multiply together those factors. So 1, 2, 3 columns here. Our greatest common factor will be just 2 times 3 times 3. So 2 and 3, that's 18 here. So 18 is our greatest common factor. So if we were reducing this fraction here, 54, that would be divided by 18 would give us 3 on the top and 2 on the bottom. And there we go. Okay, so that was the example. Let's do one more of these for me, and then one for you after. 48, 2 and 24, 2 and 12, 2 and 6, 2 and 3. And 80, 2 and 40, which is 2 and 20, which is 2 and 10, which is 2 and 5. Okay, I can see what it's going to be here already, just 16, but let's just write it out for clarity here. 48, 2, 2, 2, 2, 3, 80, 2, 2, 2, 2, and 5. And then we're just taking 1 from each column here, greatest common factor. 1, 2, 3, 4. 1, 2 times 2 times 2 times 2, and that is 16. Again, if you were doing this, if you were just writing this out for yourself, I really would not expect you to write all this. You can just kind of look at these and say, okay, 1, 2, 3, 4 2s, so 2 to the exponent 4, 16. Okay, done. Just whatever is the shortest way for you to do it, but this is, again, to show the thought process. All right, one more here, practice for you with 18 and 40. Go ahead. All right, our result here, our greatest common factor, turned out it was just 2. There's nothing else that we could do here. No larger factor than this, unfortunately. Usually we'll find a larger number, something a little less obvious than this, but in this case, doesn't always work out. So that's that one. And with that, we are done with the practice for today. Excuse me. So in the textbook, this is from the elementary algebra textbook. Chapter 1.1 has questions about divisibility tests and about prime factorization and about finding the least common multiple. And then chapter 1.5 of that textbook has questions about simplifying fractions, and that uses the greatest common factor method that we just finished, or would benefit from using greatest common factor. So there are places where you can practice all this with stuff with the prime numbers and quickly recognizing factors. Again, the math behind all of this is not especially hard. It's just being able to do it quickly that I want you to be able to recognize. Also, without a calculator. Simple numbers did not need calculators for any of this. Okay, so today, prime numbers, divisibility test, prime factorization, this vocabulary here, digits, even numbers, odd numbers, finding multiples and factors, and knowing what a prime number is. Those will all be useful terms. In the next video, we will talk about expanding and factoring with brackets and polynomials, and then we'll take those same concepts and then find ways that we can do just arithmetic shortcuts for adding or multiplying or dividing two different numbers. How can we sort of do factoring and find shorter ways or shortcuts and easy ways to kind of do these operations in our head without even needing to write anything. So more about shortcuts next time. But until then, we're done for today. Have fun with some of these practice problems that I just showed you. And I will see you in the next video. Thank you for watching.